So have a seat, please. We need to start the next lecture. Could you lecture give me a title? Please come in and sit down. Okay, let's start the next lecture. So Alexei Kitaev is awardee of the physics part of the conference. I've known him for about 6 or 7 years. When he visited Harvard CMSA, he was working with Dan Free and Mike Hopkins in those days. And they have some kind of meetings constantly each year, and happens to choose Harvard in my institute, CMSA, and so I met him. More quiet than what I thought. I'd like to talk with you more. And I was in the physics department. There was on how to recruit him to come for even a short visit. It was not easy. So I was very pleased when we the award to him. He accepted instantly, which I'm grateful that he will take this offer to come. A important you will come. He is expert on one of the founder of quantum computing and statistical physics. Subir has talked about his work on Sunday, so I would not repeat it. But we will listen to his work, which is extremely today, called Keiko. So, thank you.
Thank you for the kind introduction and for the invitation. It's a kind of toy version of a black hole. So we'll talk discussing connections between different mathematical models. But those models can shed a light on interesting physical phenomena. This is the outline. Can something unpredictable and but may not be able to predict things because and a better definition is chaos is predictability. it's like possible to make for a few days, because a small now will be amplified later month. Even is quantum chaos. Quantum chaos is less intuitive. It's described by out-of-time order correlators. We can consider the product of operators applied at different times, and those times should alternate. And this way we construct a classical and quantum. I'll focus on two systems or classes of systems. One is black holes. This is an image of an actual black hole in another galaxy, in the center of a galaxy, that can be seen from Earth using radio telescopes. Same geometry can be related to observations, but there are parts of the black hole that are hidden from sight. What happened? Oh, it's back. Yeah, thank you. I hope you from sight. And in this picture, there is a physical region and some regions inside the black hole, and the boundary between those regions, which is called horizon. Those are not seen directly, but we can study them theoretically. The next picture illustrates Hawking radiation. It's a quantum effect in black holes. As Edward Witten said in his lecture yesterday, Einstein gravity and quantum mechanics well, and to combine them, one needs a more advanced theory like string theory. However, some simple quantum effects can be studied within the framework of Einstein gravity. They do combine if we don't go to very short distances. And Hawking radiation is one such effect. Effect is called Drake-Hooft effect. It's both classically, if object into a black hole, it's gone. We never see it again. However, this object creates a perturbation of space-time inside the black hole. And this perturbation can be regarded as a shock wave, concentrated of the past horizon. Radiation particles pass through this wave, and this radiation is a wave. But it butterfly, we can detect the presence just looking at the weather around. We don't know whether it rains because of the butterfly or for some other reason. And the same is true of Drake-Hooft effect. I'll explain it later in more detail. The other class of systems that exhibit chaos is large N models, including the Alexei-Kitaev model. A large N system is a system of simple degrees of freedom, like spins of fermions interacting with each other. And they interact all to all. Every pair or every group of 4 particles are coupled to each other and interact. This is an illustration. The Alexei-Kitaev model is special in that out-of-time order correlators or chaos in that model are similar to chaos in black holes. And this is because the SYK model has a soft mode, a collective mode. We know collective modes in condensed matter systems like sound is a collective mode in a system that is built of atoms. But in this case, the collective mode is more interesting. It's a reparameterization of time. You can think of time as a spring, and I've drawn a circular time, which is imaginary time, so-called Matsubara time. And there is a collective mode that involves deformation of the time spring, and it's also related to geometry. So let me start from the beginning. The butterfly effect. Butterflies' wings can change the weather. True, because the Earth, with its atmosphere and ocean, is a complex, chaotic system. But it's too complex. Let's consider a simple chaotic system, the stadium billiard. This is a billiard, and this is the trajectory of a ball that bounces off the walls and moves without friction. And you see that the trajectory is kind of irregular. How do we understand that? To understand it, we need to first equation of motion, and those equations can be written in terms of four variables. There are two coordinates, q1 and q2, and the corresponding momenta, p1 and p2. And that whole set of four variables is the full description of the system state. The state evolves in time according to some equations. And if we consider two trajectories with slightly different boundary conditions, the difference is amplified over time such that the trajectories diverge. You see the red trajectory and the green trajectory diverge, and they diverge exponentially in time. And the exponent kappa is called the Lyapunov exponent. The exponential trajectory is the hallmark of classical chaos. This is a mathematical phenomenon. It can be seen in simulations, but is the idea chaos? The problem is the absence of reference. So pause for a moment and let you think about testing this theory. Okay. Tests. Test one. Run the Earth time or the Earth dynamics forward and backward. And we can describe a particular experiment. In the X0, advance time to t and record weather data. We run, introduce a butterfly time forward again. Compare the weather, recorded weather without the butterfly. And test two is to do parallel using two copies of the Nicholas. That's in part because the Earth is such that we cannot control. Let's this kind of test can actually on small require very precise control. If we on a classical system, the required accuracy should be exponential, such that experiment the amplified errors due to the divergence of trajectory. This requirement can be mentioned is the number of digits proportional to the simulation time. In an actual experiment, it's very hard to do. So it can only be done for very, but for longer time, exponential and then stops and effects become important. Systems more favor accuracy is n times t and this number says that there shouldn't be any error at all during the simulation, and say one phonon absorbed during the simulation. It's a requirement, but it can be met or a small system like several nuclei. Now I would like to discuss quantum. Does not necessarily remember it well. So this slide is supposed to serve as a reminder. In quantum mechanics, we have basis states and general states. And I use a system of n spins or n qubits as an illustration. Each qubit can be in state 0 and state 1. And if there are 2 qubits, there are 4 basis states. 0 should add up to 1 if we square them. The square of a coefficient is the probability of the corresponding basis state. And this is one example of a superposition. One describes states by the density matrix. It's an operator made out of the state vector, like this. And this description is more convenient to find the reduced density matrix of the first cube. Then the product mathematical construction that describes putting two small. We can states like this. We have two state vectors, state vector of the first qubit and of the second qubit, and we can define their product. Every state of 2 qubits is the product of states of individual. For example, this state is not a multiplied regardless of whether we act on product states or not. For example, we can consider the tensor product of the identity and the Pauli matrix sigma z, and we get. And in physics, the sigmas that sigma z acts on the second qubit spin. An important thing in quantum mechanics is measurement. An experiment is used in such a way that with some initial evolve it, and the evolution is governed by the Schrödinger equation. Overall, with the given time period is given the evolution operator U, and this evolution operator is the exponential of the Hamiltonian. If the Hamiltonian is time dependent, one has to use the so-called time-ordered exponential, but that is not important for my talk. After the evolution, we can measure some different types of measurements, some number, either a measurement, a yes or no measurement. We could measure the first state 1 or in state 0. 1 means specify the measurement a projector, this action operator, and quantum mechanics psi has the following probability of the measurement come yes. The probability of the yes are the matrix element. We apply the projector to psi and then multiply by psi again. Consider the inner product. Expressed like this, we plug this form, and we get the final race. And this expression, something called pi of t. It's the operator. Now, the probability is a special form of a correlation function or a correlator. And the general notation for correlators is if we have some operator A and some state, the state vector psi or the density matrix rho, and define A in brackets. We start with initial state psi. Then we apply operator X. The system evolves for time t, and after the system has been evolved, the final state is the function of the initial state of the yes outcome on paper, theoretically, and it's given by this formula, which can be expressed as a correlation function. It's the correlator of three operators: x at time 0, this is the way to describe things in quantum mechanics. Variant of the measurement protocol. We may use auxiliary qubit for it to apply. With the initial state psi in and the auxiliary qubit is used to select operators. Select x1, depending on whether the auxiliary qubit is 0 or 1. The selection process is described by a certain operator, and we get the state, then we'll let the system evolve, perform the measurement, and we get a correlation function. The important point is that the correlation function in general contains different indices, J and K. They appear when we actually have a slightly bigger system. One can generalize this, then we evolve this combined system with the combined Hamiltonian that includes some interaction between the system and the device, and the details here are not important, but depends on times, T1, TP, TS prime, and those times occur in a certain order. First, the time increase. We go up, which means we go forward in time, and then the going forward in time and then backward in time. But there are also other correlators that can be defined theoretically in 1969. And back in those times, people did not think about subtle properties of systems of qubits that can be evolved. Calculated a certain quantity for a real superconductor, which of course did not contain a model. But then they related this quantity in a normal metal, and the relation is out of time order correlators appear. This is reduced out of time order correlator. We can also introduce them by an experiment with a few qubits. Say metaphorically, we have operators describing where the measurement and the time t again, which is first the observation at time t, butterfly in time 0, observation at time t. And a quantum device can select one observation, and we get the out of time order correlators are related to classical chaos, and that was already observed by Larkin and Ovchinnikov. In classical mechanics, we have a piece of J is the momentum operator in quantum mechanics, and classical mechanics can be considered as a limit of the classical of the quantum mechanics as h bar goes to 0. And the commutator with respect to the initial, and if we know that this thing grows exponentially time, we can guess how the commutator is related to the average value of the square commutator. Then there will be some plus or minus some correction that grows exponentially in time. If it becomes strong, we can no longer between classical mechanics, and we have to solve the full quantum problem. So this is Otto in a semi-classical system. For example, fields in the vicinity of black hole, this behavior of the out-of-time order correlator. The constant grows exponentially in time. The coefficient in front of is small. The S in the denominator is the entropy of the black hole. The formula is no longer applicable. The exponential growth saturates. But A peculiar feature of black holes is that the Lyapunov exponent behaving similarly to a semi-classical of H bar. We have a small parameter 1 over S. Here, the situation with the Lyapunov exponent is more complex. The Lyapunov exponent is small. The dynamics is slow. In general, the dynamics cannot be but 2 pi times the temperature is the Schenker, Stanford, and Moldasena in 2015. The dynamics cannot be faster than that. Black holes have as possible, but the is small when the temperature is small. As the temperature goes to 0, the correction is manageable. So this is the message is that, and the SYK model have similar out-of-time order correlators. In particular, the Lyapunov exponent is the same, and analogy between these two. Now let me I'll talk about black holes, and then there's SYK model. And this is slightly more technical. This slide, of course, is not technical. It's just an introduction of which will look black in the following way. We can try to send light from the surface of that body to the space, and instead of sending light, let's first throw a ball. Escape velocity by comparing the potential and kinetic energy. The initial state, the potential energy is potential, and the kinetic energy escape velocity. At the final state, they're both 0, and this gives us this value, which we can extrapolate to the relativistic case where classical mechanics or Newtonian mechanics is no longer applicable. Somehow it gives the exact answer. It gives the gravitational radius or Schwarzschild radius A that depends on the mass of the black hole and constant. In quantum, in classical gravity, the correct way to derive this formula is to use time. The proper time, it's an element of length on a trajectory can be expressed like this. And this expression involves the gravitational potential. The Einstein, and its solution for a spherical symmetric body was found by Schwarzschild. It's given by this metric. The metric has some part that depends on time. The time, the spatial component of the metrics, and there are actually radial one and other dimensions the formula is slightly different. To understand it, you can consider that metric, or the imaginary time, instead of minus dt squared, use plus d tau squared, and write this is a Riemannian metric on some space. It has an apparent singularity at r equal to a, the gravitational radius, but it's only an apparent coordinates. So the imaginary like the polar angle, and the horizon equals a of time issues. It shrinks, but nothing drastic happens actually. It's just a singularity rather than itself. In Lorentzian, one can define lines of constant r. This is a line of constant time, and one can map Schwarzschild metric in this wedge. This wedge doesn't cover the whole left. It only covers part. And there are polar coordinates actually, and cosh instead of the sine function and the cosine function. And in the new coordinates, the new coordinates allow for extension. One can define an extended space-time, and it's called eternal black hole. This extended space-time is valid in, you may think of the space-time continuum the black hole, and he will cross the future horizon. By itself, crossing the future horizon is not a disaster, but then everything that passes through the future horizon falls onto a singularity, which is really bad. From outside, we don't see the horizon, let alone the singularity. And theoretically, one can think about other regions that are even more elusive. An important feature of the extended space-time is asymmetry. There is a symmetry that stretches everything in one direction, in the direction of the past horizon, and squeezes everything in the direction of the future horizon. And that symmetry acts on the full space-time. It acts somehow outside at large distances from the black hole, and also in the vicinity of the horizon. And one can define a parameter called surface gravity in the following way. In the vicinity of the horizon, this symmetry transformation acts as a Lorentz boost. And at large distances from the black hole, it acts as a time shift. If we divide a Lorentz boost by the time shift, we get something inversely proportional to time. And that's called surface gravity. If we multiply it by the speed of light, we'll get acceleration. And we may interpret it as the acceleration of free fall at the horizon. So this is an important parameter characterizing a classical black hole. But it's related to quantum mechanics of black hole, Hawking radiation. Hawking discovered some 50 years ago that black holes are not exactly black. They can emit radiation. They can emit photons and other particles. Most of those particles fall back down to the black hole, but some of them escape. And the radiation is characterized by temperature. It's like thermal radiation with a certain temperature related to the surface gravity. This formula has the Planck constant in it. It illustrates that the effect is quantum, but in most places I set the Planck constant to 1 because we focus on quantum mechanics more than on classical mechanics. You can see that the radiation originates at the past horizon, and most of the radiation falls back through the future horizon. Some radiation escapes. One motivation for the SYK model was an attempt to reproduce the Hawking relation between the surface gravity and the temperature. This is a very simple relation, but we would like to reproduce it in a more conventional quantum system, not referring to black holes which are not well understood. The full understanding of a black hole perhaps requires string theory or some other advanced theory. And finally, I would like to discuss another effect for black holes, the Drake-Hooft effect. Incoming particles, like if we throw something into a black hole, interact with Hawking radiation. And the interaction depends on the time interval. If we throw an object into a black hole, wait for some time t, and try to detect a Hawking radiation particle after that time t, the interaction between the incoming and undergoing object is amplified in time. This is counterintuitive. The interaction can become formally arbitrarily large. There are some limits on the interaction strength, of course, but one can think in details how one could observe this effect. This is the description of the effect in more detail. We throw a particle into the black hole. It creates some gravitational interaction, gravitational perturbation around the particle trajectory. And then we watch outgoing particles. And when we consider an outgoing particle at time t, it makes sense to apply the symmetry transformation such that the outgoing particle has a simpler description, a more natural description. But when we apply that symmetry transformation, we stretch everything in this direction and squeeze things in the opposite direction. And that makes a difference. The perturbation is concentrated near the path horizon, this purple line. And the perturbation looks like a shock wave, like a singularity in space-time. Although it's not a singularity, it's just a strongly squeezed, smooth space-time. And the radiation passing through this shock wave is delayed. This is the Drake-Hooft effect. How do we observe it? The observation is difficult because the shift, the outgoing particles experience is relative to the black hole interior. To actually detect this shift, we need a reference point inside the black hole, which is difficult. And this is similar to the butterfly effect. When it rains, we don't know whether it's due to a butterfly or not, but to make sure, to be sure that the rain is due to the butterfly, we need 2 copies of the system. And here is a potential scheme to observe the Drake-Hooft effect. We send a test particle to the black hole, but we send it the wrong way, back in time. That particle goes inside the black hole. Then we run the time forward, and while running the time forward, we drop an object into the black hole. This object creates a shock wave, and when the particle comes out of the black hole, it experiences a delay passing through the shock wave. And this way we can consider the difference between the initial state of the particle and the final state of the particle. In quantum mechanics, this effect is described using out-of-time order correlators. Now let me introduce the SYK model. It doesn't look like anything similar to a black hole. The model consists of Majorana degrees of freedom, chi1 through chi-n, which interact with each other using this quartic Hamiltonian. This model was first defined by Sajidiev and Ye, but they defined it in a more complex way. And if we want to study more complex properties of this model, like out-of-time order correlator, it will be convenient to simplify the model first. And that is the simplified version. Detailed calculations in this model were done by Maldacen and Stanford and by Sach and myself. And this simple quantum mechanical system has a collective mode equivalent to Drake-Hooft shock waves, but in 1+1 dimensions. This is a formal description of Majorana fermions. Majorana fermions are generators of a Clifford algebra. These are the defining relations of Majorana operators. One can consider representations or the representation of this algebra using the Fock space, and one can express the action of chi-j in terms of the action of lowering and raising, or annihilation and creation operators. And this is an illustration. When we apply a creation operator, we put a particle in a box, and we apply another creation operator, and we put a second particle in another box. The full definition of the SYK model is here. It's a quartic Hamiltonian, and it has random constants, random interactions. The average value is 0, but the second moment is not 0. It scales like 1 over n cubed to have a nice thermodynamic limit. And the randomness helps to solve the model. One can consider similar models with some specific interactions. They will be difficult to solve, but the random model is easy to solve. Now, let me mention some interesting properties of the SYK model. The first property is fast dynamics at low temperature. And that is why other models, many other models don't work. When we consider models like interacting spins at high temperature, the dynamics is slow because it's determined by the interaction strength rather than the temperature. Fast dynamics means that its speed is determined by the temperature. When we go to low temperatures, the system forms a so-called spin glass, and the dynamics is exponentially slow. There are other models like Fermi liquids, which have slow dynamics at low temperatures, but not exponentially slow, only quadratically slow. The SYK model is special because it's a non-Fermi liquid at low temperature, and that was the great insight by Sajidiev and Ye in 1992. And I used this model and studied it in a slightly different direction, calculating out-of-time order correlators. The model is solvable for large n, and this is the exact interval of parameters where the model is exactly solvable. It has emergent symmetries at low temperatures and large n, and it has an approximate diffeomorphism symmetry, diffeomorphisms of a circle that is broken to the group of Möbius transformations, preserving the circle. And the symmetry breaking is both spontaneous and explicit. There is no explicit symmetry breaking at zero temperature, but at any finite temperature, the symmetry is also explicitly broken. And the lower energy states are described by this coset. And in this coset, we can define a collective mode that turns out to be equivalent to two-dimensional gravity. Now let me go through a few very technical slides. This is how the SYK model is solved. It's solved by using Feynman diagrams. And one can consider the full green function and the bare green function and interactions. And the dotted line means averaging over the Gaussian distribution of interactions. One can consider various diagrams and select leading diagrams. Some other diagrams also exist, they are suppressed by negative powers of n. If we write down the diagrammatic series only including leading diagrams, it has a special structure. This diagrammatic series can be written like this, and it's already transformed slightly. I use thick lines, which include a bunch of other diagrams with thin lines. Each thick line is the sum of many diagrams. The thick line is the full green function. Then the diagrammatic series is just the geometric series with sigma given by this, and there is actually a formula. And summing up the geometric series results in the Schwinger-Dyson equation, which should be combined with this equation. And these are just functional equations that can be solved on a computer. And one can obtain a solution graphically. One can calculate the green function. But at long time intervals, a solution can be obtained also analytically. And the trick is that one term in the Schwinger-Dyson equation becomes small at low temperature. The time derivative in the Schwinger-Dyson equation may be neglected at zero temperature. And that gives the formula for the green function at zero temperature, first obtained by Sajdiv and Ye. And one can extend it to small but finite temperatures. But the most remarkable feature is the existence of a soft mode. If we look at the Schwinger-Dyson equation, neglecting the derivative term, then the solution is not unique. There are many solutions. If G is a solution, then we can construct a new G, which will also be a solution. And to do that, we change the time by an arbitrary function of f. Here I'm using the imaginary time formalism. The time goes around a circle, and the length of the circle is the inverse temperature, called beta. So there are multiple solutions. Each such solution is obtained from the zero temperature green function, beta equals to infinity, by a certain transformation. And in particular, if this phi of tau is taken simply as 2 pi over beta times t proportional to t, we get the finite temperature solution at equilibrium. But there are many non-equilibrium solutions, and there are also fluctuations. At equilibrium, one can consider a fluctuating function phi, which may be thought of as a spring of time. There is this time circle that goes around, and its deformation is described by the function phi of tau. It's a map from the circle to itself, and there is an associated energy or action that involves the so-called Schwarz chain. The Schwarz chain is remarkable because if F is a linear fractional transformation, the Schwarz chain vanishes. It has certain transformation law under fractional linear transformations. And one can go even further. One can relate the Schwarz chain action to geometry. One can consider an unrelated question, a seemingly unrelated question. Let's consider a curve in the hyperbolic plane. This is the hyperbolic plane in the Poincare disk model. It has radial coordinate r and angular coordinate phi. And we consider a curve that is pretty close to the asymptotic boundary of the hyperbolic plane. And it turns out that the extrinsic curvature of this curve in this limit, when the curve is very close to the asymptotic boundary, is related to the Schwarz chain. And this way, we can reformulate the Schwarz chain action in purely geometric terms. We have a curve in the hyperbolic plane. It's kind of like a balloon filled with air. And there are two terms in the effective action. There is an area term, or the volume of air in the balloon. And there is also length. But the length can be kept fixed. The balloon cannot be stretched. And its energy will depend on the volume or the area. And now let's consider thermal fluctuations of this balloon. It can shrink in some directions, expand in other directions. And the statistics of these fluctuations is exactly the same as the statistics of the SYK model at low temperatures. One can make an analogy to the Lorentzian signature by passing from the hyperbolic plane to the anti-de Sitter space. Now the time is real, not imaginary. This coordinate phi may be interpreted as time, but it's not the physical time. The physical time is given by these green lines. Each green line is a line of constant radius going forward in time. And each blue line is a time slice. And in this interpretation, we can talk about the butterfly effect by considering two trajectories. One trajectory on the right and the other trajectory on the left. And in this picture, those trajectories are aligned with each other. We can use the left trajectory as a reference, and we can perturb the right trajectory. And when the right trajectory is perturbed, we have some exponential growth of perturbation, and that is classical chaos. Of course, the model can also be quantized, and it will be quantum chaos. And that's the origin of the connection between black holes and the SYK model. Finally, to clarify this connection, I should say that we have talked about boundary effects. These particles going in the anti-de Sitter space are boundaries of some space-time. And we can consider an actual theory of gravity for the bulk, for the space-time itself. But such a theory in 2 dimensions is degenerate. To make it non-degenerate, we need to introduce a new field, so-called dilaton. And qualitatively, it becomes similar to the Einstein theory in free space time dimensions. However, this theory, as well as the Einstein theory for n equals 3, is rigid. It means that the bulk space-time is rigid, and all degrees of freedom are actually on the boundary. If we want to discuss the Drake-Hooft effect, we can apply some gauge transformation, some diffeomorphism that removes the shock waves and turns them into a deformation of boundaries. And this is the connection between gravity and the SYK model. So if we go the full way, we start with the SYK model, solve the Schwinder-Dyson equations, identify a collective mode, describe it geometrically as a boundary problem, and do some geometric transformation to turn into a bulk problem. And that bulk problem turns out to be a gravitational theory, although a very simple one. It's the so-called Jakiv-Tatel-Boehm theory. So I've reached the final slide. Let me summarize. Chaos is a theoretical concept. Direct experimental tests of chaos are possibly only for very small systems. Quantum chaos can be described by out-of-time autocorrelators. The Lyapunov exponent is well defined in the quantum case in certain cases, in particular for large N systems and for black holes. To define the Lyapunov exponent, we need some large or small parameter. And these are two examples where such parameters exist. The SYK model is similar to black holes in that the Lyapunov exponent is as large as possible. It's equal to 2 pi times the temperature. And finally, if you think that out-of-time autocorrelators are completely irrelevant to the real world, let me describe a related model, which was introduced by Maldacena and Chi. It's two coupled copies of the SYK model. And the calculation of ordinary correlators in this model is similar to the calculation of out-of-time autocorrelators in a single copy of the SYK model. And the physical properties of this model are remarkable. This model exhibits quantum teleportation. If we introduce some perturbation on the left, we just knock the system slightly. The perturbation seems to be gone. It kind of dissolves in the many degrees of freedom. And after a certain time period, it emerges on the right. And one can think of this process as the system secretly having some bulk that is not seen in the picture on the left. And the perturbation propagates through this bulk from the left to the right and finally emerges. And it can bounce back and appear on the left again. So this theoretical exercise of calculating out-of-time autocorrelators can lead and have led to new discoveries that may be possible to test experimentally in the future. Thank you for your attention.
Well, thank you for the great talk. Let's now have questions. Oh, there.
Thanks so much, Professor Kitaev, for this wonderful talk. I really enjoyed it. So my question is about, is it possible to implement the first test of the butterfly effect that you mentioned earlier on a quantum computer? And maybe more specifically, suppose we are able to simulate the construct a quantum circuit and simulate the forward and backward time evolution of certain many-body quantum systems, and then and we can suppose also ignore the potential errors from Schroeder product formula and the coherence errors from simulation, then can we expect how large the system is going to be to make the test work, and which kind of quantum operations could be treated as a butterfly in the simulation? Thanks.
Yes, it is possible to simulate that on a quantum computer, and it has been done in a small system with a few qubits. The gates that were applied were randomly chosen. One can choose random gates, not even using a Hamiltonian or Trotter approximation. One applies a sequence of gates, then some entangling gate, and the reverse sequence of gates. That has already been done.
Other questions? Other questions? Yeah.
Thank you for your beautiful talk. In the spectral theory, the quantum chaos describes the eigenvalues and eigenfunctions of high frequencies on the chaotic space. I want to know the large n particle system, and are there some relation between the large n particle system and the chaotic dynamical system, like the geodesic flow on hyperbolic surface? Thank you.
I'm not sure if there is an exact relation, but there is an analogy. For large n systems, 1 over n is analogous to the Planck constant. It would be nice to have a closer analogy, but I don't know how to do that.
Oh, thank you.
Okay. Other questions?
So there are similar solutions from classical consideration. If you slide inside the horizon, and the solution is not smooth, and the mathematicians can prove there are shock waves in time, but not smooth. So maybe, this phenomena can be understood with large n. So it's actually a classical phenomenon.
Do you mean classical shock waves like in a gas, or do you mean gravitational shock waves?
Yeah, so the solution is not smooth, but it has shock waves in time.
Do you mean shock waves in a gas or in a different system?
Just inside the black hole. Horizon.
Inside the black hole.
Yeah, horizon.
Yeah, you can find a solution that is not smooth, but classically, the solution appears asymptotically by the evolution of a smooth solution, and the singularity does not develop at any finite time. This is just a property of Einstein's equations.
Okay. Other questions? Yeah.
Okay, thank you for the talk. I have a question on the quantum chaos on the continuous symmetry. I'm working on math problem calculating the so-called OTOC on the toy model of black hole, the so-called hidden particle protocol, on the continuous symmetry or maybe conservation law of groups like the U1 or SUD group. But I'm always wondering, is it proper to ask such a question in the sense of physics, because maybe from the perspective of ADS-CFT and the problem to have global symmetry on black hole. So I'm wondering, is it proper to ask this question from physics? And do we have any other interesting physics model to consider on the maybe continuous symmetry, like maybe the SYK model you mentioned? Thank you.
Excuse me, I didn't understand. You asked about whether it's proper to ask some question. What is?
Yeah. I mean, because when we consider the hidden press code, we always calculate the OTOC on the dynamics with no symmetry. But now I'm hoping to ask, could we do similar things when we have continuous symmetry imposed on the system? Yeah, the symmetry of the from some group like the U1 group or maybe SUD group.
There are variants of the SYK model with symmetries. In particular, the complex SYK model has a U1 symmetry corresponding to the conserved electric charge.
Okay, we have to wrap up. So thank you very much for the beautiful talk. We have to meet on time still, 11. Sorry about that. Yeah, we come back 11.